Hi guys, I will explain the moment of area, part 3, for triangle and the circle, from second moment of area to summary. Here I have a quiz for you. One of the triangles below has different second moment of area with respect to z prime axis from the other two triangles. Which one is it? I explained the second and the product moment of area and the parallel axis theorem for rectangle in the previous video, E41. In this video, I will explain the second and the product moment of area for triangle and the polar moment area for circle. The others will be explained in the upcoming videos. Let's calculate the second moment of area for a triangle. As a step 1, we calculate the small area dA, which is the horizontal length W multiplied by the width of a strip dy. And the step 2, we formulate the equation for W in terms of the known dimensions. By similarity of two triangles, this is a big triangle and this is a small triangle, W can be expressed in this equation. And the step 3, we calculate the small moment of area Diz prime, which is the product of dA and y squared. Therefore, second moment of area can be obtained by the integration of this expression from 0 to h. Consequently, we end up with bh to the 3 over 12. By the parallel axis theorem, we can obtain the second moment of area per triangle, having the coordinate system of which origin locates at the centroid and its horizontal axis is parallel to the base of a triangle. Rearranging the equation of parallel axis theorem, we can have this equation. Here, Iz prime is bh to the 3 over 12, which I have already calculated in the previous slide, and the A is bh over 2, and the D is h over 3. Therefore, the second moment of area for a triangle in this case is bh to the 3 over 36. How about inverted triangle? To get the second moment of area for the inverted triangle, let's employ the parallel axis theorem. In the first step, we need Iz, which is second moment of area with respect to the axis passing through the centroid of a triangle, which I have already obtained in the previous slide. In the second step, the area equals bh over 2. And in the third step, D equals 2h over 3. Substituting all the terms for Iz and A and D, we can get the result bh to the 3 over 4. Let's calculate the second moment of area for a right triangle. As a step 1, we calculate the small area dA, which is the horizontal length z multiplied by the width of a strip dy, like this. And the step 2, we formulate the equation for z in terms of the known dimensions. By similarity of two triangles, here we have a big triangle and a small triangle, z can be expressed in this equation. In the step 3, we calculate the small moment of area Diz prime, which is the product of dA and y squared. Therefore, second moment of area can be obtained by the integration of this expression from 0 to h. Consequently, we end up with pH to the 3 over 12. This time, let's get the second moment of area with respect to y-axis. The whole area can be divided into two rectangular triangles, P and Q. The second moment of area for P is HB1 to the 3 over 12, and the second moment area for Q is HB2 to the 3 over 12. Then we can get the second moment of area for both of P and Q by this equation. Here we have three cases for different coordinate systems and the triangle shapes. In the first picture, z-axis passes through the centroid of a triangle. In the middle picture, z'-axis coincides with the base of a triangle. In the last picture, z'-axis passes through the vertex of an inverted triangle. The farther the centroid is from the reference axis, the smaller the denominator, as you can see here. Let's calculate the product moment of area for a right triangle. And step 1, small area dA equals z dy. By the similarity of two triangles, here we have a big triangle and a small triangle, we can formulate the equation for z in terms of the known dimensions. And step 2, we find the centroid of small area dA. Y bar equals y, and z bar equals z over 2. And step 3, using the z and the z bar expressions from step 1 and 2, we can obtain the expression on dizy prime. In the step 4, we integrate the dizy prime from 0 to h, and we end up with the final result, b to the 2, h to the 2 over 24. Now let's use the parallel axis theorem to find the product moment of area about the horizontal and the vertical axis passing through the centroid in a right triangle. Those axes are parallel to the base and the height respectively. Let's arrange the equation of the parallel axis theorem about the product moment of area with respect to the axis passing through the centroid. The centroid of a right triangle is 1/3 of the height of the vertex at the right angle to the base and the height, respectively. Substituting all the values into the equation of IZY, we can find the product moment of area about the ZY axis passing through the centroid and parallel to the base and the height, respectively. Polar moment of area is defined as antiderivative of radius r squared with respect to the area. A radius can be resolved into z and y components. Therefore, polar moment equals sum of second moments of areas to the corresponding axis. Let's calculate the polar moment of area for circle. In the first step, we assume the small circle strip and formulate the equation for small area dA, which is 2 pi r dr. In the second step, we calculate the dip, which is r squared dA. In the third step, we integrate the small polar moment dip. We finally get the polar moment of area for the circle, which is pi r to the 4 over 2. Because of symmetric shape, Iz equals Iy again equals phi r to the 4 over 4 because Ip equals Iz plus Iy. What will be the polar moment of area when the z-axis moves down and become to z prime axis? By the parallel axis theorem, Ip prime equals Ip plus AD squared. Here, Ip is what we found in the previous slide, which is phi r to the 4 over 2. And D is r in this example. Therefore, we have final result for polar moment of area, which is 3 pi r to the 4 over 2. In the other way, to find the polar moment of area, let's start with the second moment of area. By the same parallel axis theorem, we can formulate this equation. Here, Iz was obtained in the previous slide, and the area is pi r squared. Then Iz prime equals 5 pi r to the 4 over 4. There is no difference in the Iy prime because y prime axis still pass through the centroid. Polar moment is sum of Iz prime and Iy prime. Therefore, the final result is 3 pi r to the 4 over 2. This is the same result by the parallel axis theorem. What is the polar moment of area? As when the z-axis moves down and the y-axis moves to the right as much as distance r. By the parallel axis theorem, Ip prime equals Ip plus AD squared. At this time, D is square root of 2r. Therefore, we have final result for polar moment of area, which is 5 phi r to the 4 over 2. In the other way, to find the polar moment, let's start with the second moment of area. By the parallel axis theorem, Iz prime equals 5 pi r to the 4 over 4, which we got in the previous slide. Similarly, Iy prime has the same value because distance r is the same. Therefore, we have the final result 5 pi r to the 4 over 2. This is the same as 1 by the parallel axis theorem. You should be careful when you apply the parallel axis theorem. We have three coordinate systems. YZ coordinate passes through the centroid. YZ prime and YZ double prime are away from the centroid. The second moment of area with respect to Z double prime can be expressed as equation 1. You cannot use Iz prime instead of Yz and the distance p minus q instead of q. In the parallel axis theorem, I will show why this is wrong application. Iz can be expressed as equation 3 from the definition of second moment of area for Iz prime. Substituting Iz of equation 3 into the equation 1 here, we obtain the equation 4, which is not the same as the result of equation 2. Therefore, we have to remember, in the application of parallel axis theorem, Iz here is the second moment of area whose axis passes through the centroid and parallel to the reference axis. The same quotient is true in the application of product moment of area. Product moment of area with respect to zy double prime can be expressed as the equation 5. You cannot use izy prime instead of izy, and distances q minus p and k minus q instead of q and k in the parallel axis theorem. I will show why this is wrong application. izy can be expressed as equation 7 from the definition of product moment of area for izy prime. Substituting izy value of equation 7 into equation 5 here, we obtain the equation 8, which is not the same as equation 6. Therefore, we have to remember, in the application of parallel axis theorem, izy is the product moment of area whose axis passes through the centroid and parallel to the reference axis. The answer to the quiz is number 3. Here we have a summary. In various types of triangles, the second moment of area is the same for all the triangles whose bases coincide with the horizontal axis. The lengths of the bases are equal to each other, and the lengths of the heights are equal to each other. Polar moment of area is defined as antiderivative of radius r squared with respect to the area. Polar moment of area can also be obtained using the parallel axis theorem. Polar moment of area equals sum of second moments of area to the corresponding axis. If you watch the previous videos, you can easily understand the upcoming videos. In the previous video, E40, I explained the first and the second moment of area and where does their names come from. Recently, I explained the second and the product moment of area for rectangles and triangles. The next video will be conicity and plystere, part 16. The moment of area, part 4. I will explain the principal axis. Please hit the thumbs up and catch the brand new videos by free subscription. So, what are you waiting for? See you in the next video. Goodbye, guys.